So let's talk about Compton scattering. Compton scattering is another one of those really important events that happened at the beginning of the 20th century that indicated that photons were real. That light really does behave like a particle sometimes. So here's the idea. When light has a very, very, very large wavelength, it behaves like a wave. So if you send light into a metal where the electrons can go back and forth, the electron's just going to go up and down and up and down and up and down with the electric field associated with that electromagnetic wave. However, when the light has a very small wavelength, it behaves like a particle. So here we've got photons. And when you take a particle and you throw it at another particle, this particle's not going to go like that. You're going to have a collision. And so we actually get a collision like this. Light comes in, hits the electron, and then they go off at different angles. And that's what happens when we have light incident on an electron, as long as it's got a small enough wavelength to really behave like a particle. All right, so let's see what else happens in this process. So we've got this collision, and we're going to do exactly the same thing that we always do with every collision between two particles. We go through and we conserve energy and we conserve momentum. This is going to be an elastic collision because afterwards, what do we got? Well, we got an electron and we got a photon. So we're not having any inelastic. It's not like you can deform the electron. So when we go through and we want to conserve energy and momentum, well, geez, we got to know what the energy of the photon is and what its momentum is. Well, we know from the blackbody radiation spectrum and also from the photoelectric effect that the energy associated with the photon is h times the frequency. We also know, and this actually kind of came from Compton scattering, that the momentum of the photon is given by h over lambda, Planck's constant divided by the wavelength of the radiation. We can also write that as the energy divided by the speed of light in a vacuum. All right, now when you go through this energy momentum process, which I'm not going to do on the board for you right now, because it is kind of complicated. In fact, it's surprisingly complicated, but the answer is not that bad. The answer tells us that in order to conserve energy and momentum, I've got to have a shift in the wavelength. So that means that the outgoing photon has a different wavelength than the incoming one. This is impossible classically. You cannot have a wave do that. But in quantum, you can. He's behaving like a particle, and he's just going to change his energy, and whatever that requires of the wavelength, well, it's going to change. So we have a shift in the wavelength, which is given by h over mc. M is the mass of the electron. C is the speed of light. H, of course, is Planck's constant. Times 1 minus the cosine of the angle that the photon went off at. All right. So what's interesting is that this shift in wavelength is associated with h over mc. This is dimensionless. So that means that h over mc must play the role of a wavelength. In fact, it does. It's called the Compton wavelength of an electron. Now, if h over mc is really, really, really small compared to the wavelength of light, then the shift in wavelength is relatively really small. So no problem. If, on the other hand, h over mc is very, very, very large compared to the wavelength of the radiation that you're sending in to hit the electron, then this shift in wavelength is going to be huge. So the Compton scattering is determined by how big the wavelength of the light that you're sending in comparison to the Compton wavelength. All right. We'll get a large effect if the wavelength is much smaller than the Compton wavelength, and we'll get a small effect if the wavelength is much bigger. So that gives us a quantitative explanation of what is meant by what I said earlier. Large wavelength behaves like a wave, small wavelength behaves like a particle. Large compared to what? Small compared to what? Large or small compared to the Compton wavelength of the electron. That Compton wavelength is really, really, really small. 2.4 picometers. So a picometer is a trillionth of a meter. So this actually is about 100 times smaller than the atom. So you've got to send in light with a really tiny wavelength, 100 times smaller than an atom, in order to get an appreciable Compton scattering effect. But we've done it, and this is the way it comes out. So that's the Compton effect.